Hello. Today's topic, we're going to talk about magnetic flux. And Farady's law of induction. Or magnetic induction, Farady's law of magnetic induction. Okay, so the definition, BV, B stands for magnetic field. It's equal to B times the area of a loop and times a cosine theta. So let's say if we have a loop that goes like this. Okay, and we have the magnetic field that's coming out of page. Okay, like that. Right. In this case, this is theta is equal to 0 degree. Okay, so what are we looking at? We're looking at the so if you look at it in the other angle, this will be like this. This will be like that. This is the area, and in the B, right? The B, it's at 90 degree to it. Okay, but the theta that we're talking about is this one here. It's not the area, but the line that's perpendicular to the face of the area, right? So this is the line that's perpendicular to the area's face. So this theta, right, between B and this line, this is the theta we are using here. Okay, so that's, in this case, theta equals 0 degrees. So in this case, special case, this is equal to B times A. So this is in Tesla unit, and this is in meter square unit. So this is a wire loop, okay? Right, so Tesla times meter square. Now, we're going to talk about the Farady's law of induction now. Okay, so let's say if I have a wire, okay, and let's say I have, this is my magnetic field that this wire is entering. It's a constant magnetic field. Okay, this is the B field, and this wire is going in like this. Okay, it's going in, right? So he's moving this way. This wire loop is going in this way. So as it's going in the next moment, right, this wire could be somewhere, say here, right? So sometimes later, okay? So this still had magnetic field like that, right? So this is a constant B field, right? A constant B field, right? So in the beginning, right? So this is before, initially, right? Initially, the phi initial, it's equal to, so this is still theta equal to 0 degree, okay? So the line is perpendicular to the face of the area, right? So it's coming toward me. And then the magnetic field is also going into the face. So they are parallel. So that's theta equal to 0 degree in this case. So this is equal to B, and this is the A, right? A is the area of this wire loop. So it's equal to B times A, and then cosine 0, which is equal to 1, okay? So cosine is 0 degree. And that's equal to 1, okay? Now, but in this case, the A, inside the A, there's no magnetic field, right? So in this case, this area is 0 here, because it's not overlapping with the magnetic field. Now, as it comes in, now this area that we're talking about is this area now, right? This area is increasing, okay? So in this case, there's no overlapping, right? So this wire, right, this area is not, right, overlapping, overlap with the B, okay? So in this case, this A is 0. So it's the one that overlapping, right? That the magnetic field need to actually going through the area, right? But this is not going through. There's no magnetic field here. So that's 0. In this case, we have area that's increasing, right? This area is increasing here. So the phi F is equal to B times this smaller a, right? So that's called that A prime, for example, right? So we got this A prime right now, okay? And that's still cosine 0 degree. So the delta phi B, right, is changing, it's increasing, and that's equal to phi F minus phi I, all right? Okay, in this case, this is equal to B A prime minus 0. So that's equal to B A prime. And let's say we have a delta T here. Delta T, let's set that to 1 second, all right? So what does the Farady's law of induction say is the following, right? The induced, this is the induced EMF, right? So this is EMF. It's equal to minus of delta phi delta T, okay? All right? So then what does this one mean? It means that if I'm increasing the phi B, right, which I am, so then the induced voltage, so that you have induced current, right, will be in such a direction that it's countering this change. So your phi is increasing, right, as you move this way, right? So then I need to have a current, induced current that's going this way right now, right? Going this way. This is my induced current. This is my induced current. So if you use your right-hand rule now, this induced current will produce magnetic field that's out of phase, right? Everywhere you go, right? On the top, out of phase, right? So then this will be inside, will be out of phase. This magnetic field that's induced will be out of phase. Okay? You see this is out of page, but original, this is called a B original, right? The B original is into the page. This is into the page. But my B, this one here, the orange one, this is B induced. This one is out of page. Okay? So that negative sign is telling us that if you are increasing, which we are, we're increasing the phi as we move this way to the right, then the induced magnetic field will be countering, right? Will be countering, right? Will be countering. So going against the increase. So we're trying to reduce it. So since the regional flux, the regional B is going in, so then my induced B need to be going out. So then I can counter it. Okay? So that's this negative sign, it's the countering. Okay? So you can calculate this case in this induced EMF will be equal to B times A prime and then divide by delta T. And let's say delta T is equal to 1 second, and A prime, let's say this A prime here, let's say is equal to 1 meter square. And let's say B, right? This is B original, this is B original. It's equal to 1 Tesla. Okay? So then my epsilon induced will be equal to minus delta phi, right? So this was 0 and become that. So that's from 0 to 1. So 1 minus 0, right? Remember? Before, right? And then divided by delta T. So it's minus 1 volts. All right? So it will be minus 1 volts going this. So this will be like that. It will be positive here, negative here, right? So on this wire, I will have induced epsilon going. So the positive will be on this side, the negative will be on this side. Okay? And that's my induced EMF. All right? So that's all we have. Until next time. Bye-bye.